All right, guys, quiz should be about closing out by now. I did actually switch over to screens here. So if you're looking, you should be able to see my whiteboard here. So we can go ahead and get started. I was tracking your progress on that. Looks like pretty much everybody who's here was participating, which is good. And generally speaking, it looks like you guys were doing pretty well on those problems. So that's good. You guys are getting this stuff figured out. It looks like you're getting Chem 101 down nicely. So good on you guys. Kudos to all of you. All right, so next thing. We want to continue working a little bit with isotopes today, which is kind of what we introduced in last night's video when we talked about the various isotopes of carbon, for example. So we could have carbon-12, carbon-13, or carbon-14. Now remember, when we're talking about an isotope, in that case with carbon, we're talking about carbon atoms because remember the identity of an atom is going to be defined by how many protons it's got in its nucleus. Okay, and carbon always has 6 protons in its nucleus. So if I see that, I know I got a carbon atom. What varies, of course, in the nucleus to define the isotope is the number of neutrons. Okay, so if I have a carbon-12, I got 6 neutrons in there. If I got a carbon-13, I got 7 neutrons. If I got a carbon-14, I got 8 neutrons in there. Okay, so the mass of the atom in AMUs can vary depending upon the isotope. Okay, so just a real quick review. If I had, for example, cobalt-60, and I could represent it this way. Somebody asked about the mass number during the quiz. And that's that number on the top left up there. Okay, so that's the total mass in AMUs of that atom, all right? So basically that's the protons plus the neutrons. So if I look at this thing, sometimes you could also say, if I'm dealing with a cobalt atom, I could put this little 27 down here as well. Now that represents the number of protons in the nucleus. And usually we leave that out because if I know I'm dealing with cobalt, I know that's going to have 27 protons in the nucleus, but you can put it in there. And again, if the atom had a charge, that would go in the top right. But in this case, we're talking about a neutral cobalt atom. So if I see a symbol like this, that's what it's telling me. I'm dealing with an atom of cobalt-60. So how would I calculate the number of neutrons? Well, that would be easy to do. So the number of neutrons is just going to equal to the mass number, which is the 60, minus the number of protons, which is the 27. The difference has to be the neutrons in the nucleus. And that turns out to be 33 neutrons if I did my math right there. Okay, so you can always figure out how many neutrons are going to be in the nucleus of a given isotope that way. All right, everybody good so far? All right, assuming so. Okay, now the next thing that we want to talk about is how do we actually get to that mass number in the periodic table? Okay, so if you go to the periodic table, what you're going to see, and I'll show for carbon what you would see. I've got a periodic table right here. You'd see the symbol for carbon there, and you would see a 6 above it. Okay, and that 6, of course, is going to represent the number of protons. We say carbon is element number 6. That's the number of protons carbon's got in its nucleus. And then there's a number underneath the carbon. Looking at my periodic table here where I'm lecturing, that's 12.011. Okay, what do you think that number represents, guys? Any ideas?
Atomic mass?
Yeah, it's probably going to be your mass of the carbon atom in AMU. So I'm just going to put AMUs under there. Okay. Now, how come it's out to a number of decimal places like that? What do you think that really represents? You're right. It's the mass of a carbon atom in AMUs. But what more specifically can I say about it? What kind of mass is it? Is it a mass of a specific carbon atom or is it more like an average mass?
It's an average.
Yeah, it's an average mass. You're exactly right. So how do you think I would get at that number? I mean, how would I calculate an average? Let's say I want to calculate the average of a mass, average mass of say 3 pieces of chalk. What would I do? Well, I would weigh each one, right? So I'd have 3 individual masses, 1 mass for each piece of chalk. And if I wanted the average mass, what would I do? How do you calculate?
Divide by the number of.
So you add up the masses and divide by the number of things you've got. So I'd have 3 pieces of chalk. So I'd add up my 3 masses and then divide by 3, and that would give me the average mass. Make sense? So that's how we calculate averages. So There's one other thing we have to think about, though, when we're dealing with average masses of atoms. And that is, we have to worry about the abundance of each individual isotope that we've got. Okay, because I think I mentioned in my video when we talk about the carbon isotopes that the most abundant isotope is carbon-12, and that's about what 99% of all carbons are carbon-12s. Then you get to carbon-13, and maybe a little less than 1% of all carbons are carbon-13s, and then there's a trace number of carbon-14s. So what we end up having to do to get at that 12.011 numbers, we can't just add up a bunch of carbons and, well, there's no way of actually doing that and then dividing by the number we've got. We actually have to do this as a weighted average. And we have to account for in that weighting the relative abundance of each one of those isotopes we've got. Okay, so here's the equation that we use. We can say that average mass in AMUs, those are atomic mass units. Remember what an AMU is. It's by definition 1/12 the mass of a carbon-12 atom. And that's just a definition we use. And it's a convenient definition of mass to use if we're talking about really, really tiny things like atoms or molecules. Okay? Now, here's how we do it. The average mass turns out to be the summation. So that's a summation sign. If you see something that looks like that, it tells me that I'm going to have to sum a bunch of stuff together. So what I'm going to do is I'm going to take the sum of this quantity. It's going to be the fractional abundance of the isotope times the isotope mass. Okay? So I would do that calculation first inside of the brackets for each individual isotope that I've got. So for carbon, I'd have to do it 3 times, right? I'd have to do it for carbon-13, carbon-12, and carbon-14. And then what I would do is I would sum those 3 up. And that would end up giving me the average mass. So that's how I calculate a weighted average. It's a little different from a regular average that we might do. Okay, so you're going to see how this works here in just a moment. Probably the easiest way to show it is to actually do it by way of an example here. Okay, so if you take a look real quickly at example number 1 here, we're going to talk about magnesium. Okay, so magnesium has 3 isotopes, which I give you down below. It's magnesium-24, magnesium-25, and magnesium-26. And I want to calculate the average mass of a magnesium atom in AMUs as I would find it in the periodic table, just like we talked about here for carbon. So what I give you is some information here. I give you mass information in AMUs. Okay, so magnesium-24 is actually 23.985042 AMUs. So notice it's really close to 24, but it's not quite 24, and that's because we're measuring in AMUs as opposed to the individual masses of protons and neutrons. Okay, but you're going to come real close to 24. Magnesium-25 has a mass, it's 24.985 and change, and then magnesium-26 has a mass that's really close to 26 AMUs. And then notice that I have a relative abundance of each one of those. And I write that as a fractional abundance. So the 0.7899 there for magnesium-24 is the same as saying that that one is 78.99% abundance. Okay, so I'm just basically undoing the percent and showing that as a fractional abundance because that's what we use actually in the average mass calculation. We don't use percents, we use fractional abundances there. But you can see that's the same as saying 78.99% abundant. All right, so what am I going to do? I'm just going to apply the equation that you see up above. Okay, so I'm going to basically just calculate an average mass for each one of these things and sum them up. Okay, so we'll do it for magnesium-24 first. Okay, so it basically tells me I have to take the fractional abundance, which is 0.7899. And I got to multiply that by the actual mass of the isotope, which is 23.985, keeping all those sig figs, and there's a lot of them, 042. And that's going to be in AMUs. A fractional abundance doesn't have units. If I multiply that out, I get 18.94. And we'll keep track of our sig figs as we go. 57, this is what the calculator gives me. 8498468, I think. It's a lot of numbers. Okay, so let's just keep track of our sig figs as we go. Notice that we're multiplying here, so we're going to be limited by the fractional abundance to 4 sig figs. So I'm just going to underline those 4 significant digits there. All right, so let's do magnesium 25. So that's the same thing. Let's use our fractional abundance here, 0.1000. It's basically the same thing as saying 10% abundant, right? Times the mass, which is 24.985837 AMUs. Okay, and work that out to get 2.4985837. Again, taking way more digits than I'm going to need. Again, I'm going to be limited to 4 sig figs. So that's going to take me all the way out to the 8 there in the thousandths place. And then we got magnesium 26. Same thing. 0.1101 abundance, that's 11.01%, times our 25.982593 AMUs. And you end up getting 2.860. Make sure I get all those digits here. 6834 AMUs. And again, check your sig figs here. It looks like we're good to 4, so I'm out to the 0, which is in the thousandths place. Okay, so I've basically done everything except sum everything up. So I've got basically the AMU mass of each one of these things. Now what the formula tells me to do once I've done it is to take the sum of them. So I'm going to add them up. Okay, so if I add all these up in the column, I'm going to get 24.30505. This is what the calculator tells me, 187 AMUs. Okay, but now we have to be careful. Which set of rules do we use sig fig wise here? Because now we're adding, right? So we're adding down a column. Everything there has 4 sig figs. But to what place am I going to be good to in terms of significance here if you use your addition and subtraction rules? Am I good to the nearest 10th, 100th, 1000th? Where should I be?
100th.
Looks like 100th. Yeah, you're exactly right. So 2 places past the decimal point. And that's defined by that guy right there, the 4 in the first one, right? I've got significance to the hundredths place there. I actually go to the thousandths in the others, but since I have no significance to the thousandths in that first one, I'm only good to the hundredths. So what that means is I'm going to actually bring my significance to that. And if I wanted to actually rewrite it to the correct number of sig figs, I would write 24.31 because I got to round up, don't I? AMUs. Okay, so that should be really close to what you see in the periodic table as the average mass of a magnesium atom. And again, this is all based on the information that was given in the problem. So my periodic table here, yeah, that's pretty much where it takes me, is out to that very same decimal point. Now your periodic table may be a little different, again, depending upon where they got the data from. Okay, any questions about that, guys?
I have a question.
Yeah, please go ahead.
So after you do the multiplication and everything, and when you're about to add them,
Yeah.
So do you round up at that point, or do you wait until after you have the sum to round it?
Good question. You round at the very end. So
Okay.
don't do any rounding until you hit the sum.
Okay.
Yep, and that's to eliminate what we call rounding error. So as a matter of fact, if I have all those digits in those multiplication steps and I'm going to sum them, I'm going to sum all those digits I've got all the way out as far as I can go, right, for each of them. I'm going to type into my calculator all those numbers in my sum. And that's actually, see where I actually have the sum down there? That's leaving all those numbers in there doing no rounding. And then at the very end, that's when I round. And the reason we do that is because if we round at each step as we go, that rounding error will actually propagate. Okay, so that's why we don't round until the very end. Make sense?
Yes, thank you.
Perfect. Very good question, actually. All right, there's lots of different forms of this kind of problem that you're going to run into. So I just wanted to show you another one here. And again, it just comes down to basic algebra that you sometimes have to do. So here in example number 2, what we want to do is calculate the mass in AMUs of silver 109. So that's one specific isotope of silver from the following data table and the periodic table. Okay, so here's a comparable table that I gave you before, but notice something is missing. Okay, so I've got everything I need for silver 107, but for silver 109, I'm missing the mass, aren't I? Got an abundance there. So what I want to do is set up some kind of an algebraic relationship that's going to allow me to get to the mass in AMUs of silver 109. Now we know it ought to be a number really close to 109, right? But it may not be exactly 109. Because again, look to the left at silver 107. Is the number exactly 107? No, it's 106 and change, right? It's really close, but it's not exactly 107. So again, my silver 109 should be something really close to that, but it's not going to be exactly 109. I want to figure out how many sig figs as I would need, what that number should be. Okay, so here's how I set it up. It's really just utilizing algebra coupled with that equation I gave you. So I know what the total average mass of a silver ion is. I can go to the periodic table and get that, right? So I did exactly that. I know the total mass, accounting for all the isotopes. So my periodic table tells me that's 107.87 AMUs. Okay, so that part's from the periodic table. That's the number up under the silver symbol there. That tells me the average mass of all silver atoms, accounting for all the isotopes. Okay, so that's what we just calculated in the last problem. So now we know that that's going to be the weighted average of the two isotopes. So I'll do silver 107 first because I have everything I need for that, right? I have 0.5184 as my fractional abundance. I'm going to multiply that by the actual mass of the silver 107, which is 106. And again, keeping all those sig figs. That was actually a measurement somebody made. I can track the units as I go. Now I'm going to add to that the fractional abundance of the silver 109, which is the 0.4816. And that gets multiplied by the actual mass of the silver 109. Oh, but I don't know that. So I can let that be by variable, which I'll call x. Okay? So now what I can do is just sort of go through my math rules, right? It says the first thing I'm going to do is I'm going to multiply those numbers together. And if I do that, I end up getting 55.4196. And again, that's what the calculator gave me. So I'm going to carry all that through. That's in AMUs. Okay. So now what do I do? What does my algebra tell me I have to do? Well, I have to take that to the other side, don't I, and subtract it. So I'll just show you the step here real quick. It's 107.87 AMUs minus the 55 that I have to take to the other side, or as we like to say, add it to both sides, right? That new math gets me every time. And that's all equal to 0.4816 times x. And of course, what I want to do is solve for x. Okay, so what do? How do I take the 0.4816 to the other side? Well, I divide both sides by it, right? So I can take that difference there, and my x turns out to be, when I do it, 52. This is the difference between the 107 and the 55. Turns out to be 52.4504 AMUs. And let's just keep track of our sig figs as we go here. This one is actually going to be good to, looks like we're good to the hundredths place there. So I'm just keeping track as I go. And I want to divide that by the 0.4816. Okay, so notice that doesn't have a unit. So I'm left with AMUs as my unit. So I've got four sig figs in each case. So my mass needs to be also good to 4 sig figs. I'm not going to round until I get to the very end. And when I do this, I get 108.9 AMUs. Okay, and notice that's really close to the 109, right? And that's exactly what I would expect to get. So again, this is a kind of variation on this problem that you would sometimes see. All right, so any questions about that, guys? So we got, about 10, 11 minutes. Let's pop over and do a couple examples over in Chem 101. And there's another one very similar to this that has a bit of a twist. And if you guys have any issues with it, ask me. Okay, so I'm just going to pop out of here and we'll just go back over to Chem 101 here. And I want in class, and for some reason I got this in chapter 1. I don't know why. It should be in chapter 2. And I think I have 4 questions here. Some of them are really easy, but I think it's that last one will be kind of interesting. Number 3 is kind of fun too. And hint, hint, you don't actually have to do a calculation for it. Yeah, it looks like 4 is a little easier than I thought it was. Before we head out, guys, I just wanted to make a mention of number 3. That one's kind of an interesting problem. It's talking about antimony there, and it's giving you the average atomic mass of it. It's 121.76 Amuse. That's the number you'd find in the periodic table. Tells you got 2 naturally occurring isotopes, antimony 121 and antimony 123, and it gives you abundances. And it asks you, in a sample of 100 antimony atoms, what's the probability that a single selected atom has a mass that's the same as the average mass of 121.76? And the answer to that is it's a 0 probability, okay? Because each one has to either be the antimony 121 or the antimony 123. The 121.76 is the average, okay? So neither one of the specific isotopes can have the average mass, because remember what the average mass is. It's a weighted average of all the different isotopes that you've got. So you can't actually have an atom that's going to have that exact mass, because again, that's a weighted average of all of them instead of talking about a very specific isotope there. Does that kind of sort of make sense? And it's kind of interesting because it's a different thing. If you weren't doing a weighted average, you could say statistically, okay, one of these things could actually have that mass, but when you're dealing with a weighted average, that can't happen. Okay, so that's just kind of an interesting little question I wanted to throw out at you guys. Any other questions from you guys before we head out?
Why
Everybody
does
good?
antimony not have 122?
Why would it
in
not
that?
have a, well, let's see. Well, because it can't, right? Look at your different isotopes that are there. One of them has to be 121, which means it has to be really, really close in AMUs to that number, and the 123. And
No,
your,
I mean, like in general, like in nature, why is there not 122?
why
Like it
isn't
skips
there?
from.
It has to do with stability. So isotopes exist because they happen to be chemically stable or physically stable, actually. And indicator of that is like if you have like a radioactive isotope, like for example, carbon-14 is a good example. It's a radioactive isotope. It exists, but it exists at a very, very low abundance. And the reason for that is because it's not very stable in nature. So the reason why there isn't actually an antimony 122 is because it's just not a stable isotope.
Okay,
So
thank you.
there are physical reasons why it can't exist. And that gets down into particle physics, which is beyond my pay grade. All right, guys, and just a quick reminder, remember to watch, I think it's video number 4 for Monday, and we'll have another 5 for 5 quiz on Monday, and you guys all have a great weekend.
Question, when will the video for today post?
Today's video will post at some point this afternoon, probably when I go home.
Okay, thank you.
But it'll be up. It'll be up by the end of today.
I just had a question about the quiz.
Sure.
How does 1 kilogram of pure gold? I thought the density would be higher.
That's a good question. It asks for like the difference between like a gram and a kilogram or something like that.
Well, it says which will have a higher density, 1 gram of pure gold or 1 kilogram
1
of pure
kilogram
gold.
of pure gold. Okay, yeah, that's a good question. Now, here's the deal. Remember that density is a property of matter. It's a property of gold, okay? And what that means is it doesn't matter how much of the gold you have. If I have, say, a 1 gram sample of gold, or I got a 1 kilogram sample of gold, it's still gold, right? And remember, density is a property of the substance, and it doesn't matter how much of the substance you've got. It's by definition
Yeah,
the
but
amount of mass associated with 1 cubic centimeter of that material, right? So yeah, the 1 kilogram sample is heavier because you got more gold, but the density is the same because density is a property of gold. Make sense? Because look what's happening. Your mass and your volume are increasing proportionally as you go from a gram to a kilogram, but the ratio of the two does not.
okay.
So that's an example of a
like-
property that doesn't depend on the amount of stuff that you've got.
Okay. I mean, I just made like volume constant. I was like, well, it's pretty obvious that 1 kilogram would have a higher density, but
But is the volume constant?
well, I I just assumed so.
And that if that were the case, you would be changing the element to something heavier, and it wouldn't be gold anymore. So yeah, think about that. It's actually a really interesting question, but density is a good example of one of those properties that doesn't matter how much of the material you've got. It's essentially just a property of the material itself.
Okay.
Volume is not, mass is not, but you put them together in density and they're independent of the amount of the stuff that you've got, right? I mean, if you think about it in terms of water, okay, water's density is a gram per milliliter. Doesn't matter how much water you got, it's still going to be a gram per milliliter in terms of its density, right? So even if you ratioed, let's say you took 10 milliliters of water and you weighed it, you'd get 10 grams of water, and the 10 over the 10 still cancel and give you the 1 back again. So it doesn't matter, and the gold will work the same way.
All right.
Make sense? That's
Yeah.
a good question. All right, I'll see you on Monday.
Yep. Thank you.
You're welcome, sir.